everyone, in this video we can discuss about synchronous counter and its design rules. In the previous video we have discussed about that asynchronous is a ripple counter and the design of different ripple counters. Okay, and we have already seen the difference between the asynchronous and synchronous counters in our previous video. And in synchronous counters, they are actually faster than our asynchronous counter, but the design is very difficult comparing with asynchronous counter design. This synchronous counter design will take some more steps. This is somewhat complicated design, okay, but it is far faster than our asynchronous counter. So this is a 3-bit synchronous counter, 3-bit synchronous up counter. Okay, so see here we have, it is 3-bit or mode 8 synchronous up counter. Okay, 3-bit because it can store 3-bit using 3 different flip-flops, and using 3-bit pattern we can generate 8 different states. That is why mode 8 counter. Okay, both are same. 3-bit up counter or mode 8 up counter. Okay, so here first one, this is a JK flip-flop, another one and the third one, all are connected with the same external clock pulse. That is why this one is synchronous, and we are considering negative edge triggering. That is why this bubble and arrow mark. So here that all the J and K are always kept it as high, so it will toggle whenever it is triggered. See, the first flip-flop is triggered directly by this clock, and second flip-flop, its clock is designed like this, the output of first flip-flop as well as that external clock. These two together, or these two are considered as input of this 2-input AND gate, and its output trigger the second flip-flop. And what about the third one? The output of second flip-flop, output of first flip-flop, and that external clock. All these three form that input of this AND gate. Output of this AND gate trigger the third flip-flop. And we have to consider output A, output B as well as the 3. All the 3 together as our output pattern. So this is an up counter, and 3-bit, it will count from 0 to 7 and it will repeat after 7. Okay, 0, 1, 2, 3 up to 7, and it will repeat 0, 1, 2, 3. Okay, so the binary pattern corresponding to these 8 different states are 0, 0, 0, 0, 0, 1 up to 1, 1, 1. Okay, so this is the timing diagram corresponding to the given block diagram of 3-bit up counter, synchronous up counter. This is our external clock pulse, and here we are assuming negative edge triggering. So this is the negative edge of our external clock. Okay, so during the negative edge of your external clock, that external clock directly triggering your this A flip-flop. So it will trigger, or it will change, or it will toggle during the negative edge of your external clock. So that's why initially A is assumed to be 0. So it is toggled to high. During the next clock cycle, next negative edge, it toggle back to high to low. Again in the next negative edge, low to high, high to low, low to high, high to low. All this happen during the negative edge of your external clock. And what about the B? When will this B flip-flop trigger? This is triggered whenever this AND gate output become 1. Whenever this AND gate output become 1, if both clock and that first flip-flop output together equal to 1, this AND gate output become 1. Then this will trigger our second flip-flop B, and it will toggle. Okay, so if both A output negative edge and external clock negative edge, the B will toggle. Again, the negative edge of external clock, and where it is, our A output negative edge here, and again this one external clock negative edge here, this is positive edge. Okay, so here we will not toggle, but here see the clock external clock negative edge and output A's negative edge comes together at the same moment, so our B toggle back to 0 from high state. Again this point, negative edge of clock, negative edge of A output comes together, so again B toggle back to 0 to high. Similarly here, negative edge of clock, negative edge of A output, it toggle again. Okay, and what about the second AND gate? Our second AND gate output become 1 if 3 input of this AND equal to 1. What are the three inputs? External clock, A output from first flip-flop, B output from second flip-flop. All the three come together equal to 1, then and this particular 3 input AND gate output become 1. That will trigger the negative edge of that particular clock pulse will trigger this flip-flop. Okay, so during the negative edge of clock, A negative edge as well as B negative, where it is, here it is B is positive, so here C will not trigger. So but here see at this point B's negative edge, A's negative edge and external clock's negative edge comes together, so C will toggle at this point. Okay, and again at this point see external clock negative edge, A's negative edge, here it is B's negative edge, C again toggle. So in the first clock pulse, what is that stage? A equal to 0, B equal to 0, C equal to 0. In that next clock pulse, A is 1, B is 0, C is 0. Initially it is 0, 0, 0. Now it is 0, 0, 1. Here 0, 1, 0. In the third clock pulse, here it is 0, 1, 1. Here it is 0, 0 and so on. Here actually that synchronous counter design is directly given the block diagram. Okay, so we have predefined set of rules, or we can solve this in the synchronized counter design as a problem. We have to follow a certain set of steps in order to generate that that synchronous counter design, or in order to generate that block diagram of a particular synchronous counter, we can follow certain steps. That's why we can consider this synchronous counter design as a synthesis problem. We have a set of steps. We can follow that steps one after another, and we can design that block diagram or the circuit diagram of any of the synchronous circuit. So consider one example. So consider a 2-bit or mode 4 synchronous up counter design using JK flip-flop. So we can first understand what are the different steps for this design problem, synchronous counter design problem. Okay, so this is we are going to design a 2-bit synchronous up counter using JK flip-flop. So first, how many flip-flops are required? 2 flip-flops. You have to fix the number of flip-flops required for the design. Here 2-bit means 2 flip-flop. Mode 4 means this counter can generate 4 different stage. For generating 4 different stage, how many bits are required? Minimum 2 bit. That's why 2 flip-flops. Now we can memorize or note down that excitation table of JK, because here we are going to implement the circuit using JK flip-flop. This is the JK flip-flop excitation table. Next, we need to understand that state transition diagram like this. This is an up counter and 2-bit up counter. So, what are the different states? 0, 0, 0, 1, 1, 0, 1, 1. So, how will it how will this that state transition takes place? 0, 0 to 0, 1, 0, 1 to 1, 0, 1, 0 to 1, 1, 1, 1 to 0, 0, and this will repeat. So this is the state diagram for this up counting, 2-bit up counting or mode for up counting. So from this, next step is that important portion of this design problem, derive the circuit excitation table. So here you have to refer this JK flip-flop excitation table and you have to mark that Q1, Q0 indicate your present state and Q1 star, Q0 star indicate the next state. That is Q1, Q2. Here it is Q1, Q2, Q1 star, Q2 star. Okay, this Q1, Q2 indicate present state, Q1 star, Q2 star indicate next state. Okay, suppose here it is 0, 0. Present state is 0, 0. From the state diagram we know that after 0, 0 it will go to 0, 1. So next state is 0, 1. So here you have to write all the 4 possible combination in order 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 different possible state in order. Then suppose we are now in this 0, 0 state. So the next state will be 0, 1. Suppose here we are in 0, 1. Next state will be 1, 0. Suppose we are in 1, 0. Next state will be 1, 1. And suppose we are in 1, 1. The next state will be 0, 0. It is clear from that state diagram. Okay, now you have to derive J1 K1, J2 K2. J1 K1 is the 2 inputs of your first flip flop, J2 K2 the next 2 inputs of second flip flop. Here you require total 2 flip flop. That's why J1 K1 first set of input, J2 K2 second set of input, and you have to fill this column. 4 columns. How this possible? You have to refer this excitation table. Suppose Q1 is 0, Q1, present Q1 is 0, next Q1 is 0, 0, 0. So identify the row that satisfying the condition 0, 0. Present is 0, next is 0. And what is the combination for J and K? 0, don't care. So you have to put 0, don't care here. Next, present state of Q is 0. Next state of this Q1 is 1, 0, 1. So refer this excitation table. Here it is 0, 1. So you have to put J equal to 1 and K equal to don't care. 1, don't care. And present state of Q, Q1 is 1. And next state of Q1, Q1 star is 1. 1, 1 means you have to put don't care 0 in J and K. Don't care 0 here. And if it is 1, 1, 1, 1 means don't care 0. Suppose, sorry, not 1, 1. Present state of Q1 is 1. Next state of Q1, that is Q1 star is 0. 1, 0. 1, 0 means what? Don't care 1. You have to put don't care 1. Similarly, refer these two columns Q2 and Q2 star and identify the corresponding JK pattern. 0 here, 1 here. 0, 1 means 1 don't care. 1 don't care. 1 here, 0 here. 1 here, 0 here. And you have to put don't care 1. Don't care 1. 0 here, 1 here. 0, 1 means 1 don't care. 1 don't care. 1 here, 0 here. 1, 0 means don't care 1. So, this is the step. Refer to the excitation table and compare present state and corresponding next state and identify the row and fill that input combination from this excitation table. Now we have this J1, K1, J2, K2 columns. Now you have to simplify using K-map. How many entries? Total 4 variables. Sorry, 4 rows. So we have to simplify using 2 by 2 K-map. 2 variable K-map. What are the variables? Q1, Q2. Okay. So you have to get expression for J1, K1, J2, K2. Okay. So for J1 and 1 K-map for J2. Next for K1, K2. Okay. So for J1 you have to put this value 0 1, don't care, and simplify this. We'll get expression like J1 equal to Q2, K1 equal to Q2, J2 equal to 1, K2 equal to 1. So these are the input for J1. What are they? J1 equal to Q2, K1 equal to Q2, J2 equal to 1, K2 equal to 1. How can we draw that block diagram for this particular 2-bit synchronous up counter? 2 flip-flops, and you have to mark Q1 complement output, Q2 complement output here J1 K1 and J2 K2 here. You have to supply that common external clock pulse to both first and second flip-flop. How to connect J1 and K1? From that previous expression, from that simplification, we know that J1 equal to Q2, K1 equal to Q2, J2 equal to 1, K2 equal to 1. So we can connect J1 equal to Q2, that output of second flip-flop, to both J1 and K1, and J2 and K2 directly connect to high voltage. Now this will act as 2-bit, this circuit will act as 2-bit synchronous up counter that will count 4 different states and it will repeat this counting. Okay, so this is about 2-bit up counting. Now this is another case, synchronous mode 6 counter using JK flip-flop. Design a synchronous mode 6. Mode 6 means it will count 6 different states. What are the different states? 0, 1, 2, 3, 4, 5. After 5, it will move back to 0. So this is the different states possible in mode 6 up counter. So how many flip-flops are required? For the mode 6 counting, we require minimum 3 flip-flops. Using 2 flip-flop, we can represent 4 different states. But here we need 6 different states. So minimum 3 bits are required. Some of the states possible using 3 bits are useless here. Still, we need 3 flip-flops. And this is that excitation table of your JK. And exactly as we have done our previous example, draw that 6 possibilities: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay, and what is that next state corresponding to these? Suppose we are in 0, the next state will be 1. From 1, it will go to 2. So next state is 2. If it is 0, 1, 0, next state will be 0, 1, 1. If it is 0, 1, 1, next state will be 1, 0, 0. Okay, if it is 1, 0, 0, next state will be 1, 0, 1. If it is 1, 0, 1, next state is 0, 0, 0. It is clear from this state table. Okay, then refer that excitation table. You have to fill JC, KC, these 2 input corresponding to that 1 flip-flop. Okay, and JB, KB corresponding to next flip-flop, and JK corresponding to input corresponding to the third flip-flops. Now you have to simplify all the 6 using K-map. Which K-map? You have to use that 8-cell K-map here because of 3 variables. Okay, and you have to put these values. First one is for JC, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. Next is don't care, and for that remaining 7 and 8 you have to put don't care again. Using 3 variable we can generate 8 different states, but we are make use only 6 states here because this is mode 6 counter. Okay, so after the 6, 2 more states are possible. In that case, for corresponding to that mean terms, you have to put don't care in the K-map. And simplify, you will get an expression like JC equal to BN and CN, KC equal to AN, JB equal to CN bar AN, KB equal to AN, JA equal to 1, KA equal to 1. Okay, this is means Ka equal to 1 means you can combine all these cells together in a single group. Now this is the diagram corresponding to that expression. 3 flip-flop, JAKA, JBKB, JCKC, AN, BN, CN are the output, and the same common clock, external clock, and JC is BN and CN. JC means BN and AN. This is not CN, this is actually BN and AN. Okay, not CN, this is actually AN. See, this is clear, BN and AN. Okay, and KC means AN. So KC you have to connect AN here in KC. And what about JB and KB? JB means CN bar AN. Okay, so you have to take CN bar as an input of this NAND gate, and gate here, and AN as another. So output of this AND connected to JB. And what about KB? KB is AN directly. And JA and KA is equal to 1. So you have to connect these two to high voltage. You can connect these to high voltage. That is why this 1 and 1. So this is that circuit diagram or block diagram corresponding to mode 6 synchronous up counter. And the synchronous counter has one more important property that is not possible in case of asynchronous counters, that is irregular counting. Suppose you need to count a certain given set of pattern, you can go for this synchronous counter design. Suppose this is the given pattern 0 0 1 0 1 1 0 0. Given pattern means this is not in order. In asynchronous counter it will count like 0 1 2 3 4 5 etc. in order. And it can also possible to count like 5 4 3 2 1 0 and repeat. All the terms are in order, but sometimes you have to generate certain pattern that is not in this particular usual order. Here see this order, this is equivalent to 0, this is equivalent to 2, 3 and 1. This is that given order, but this is not in that usual normal order. Okay, so using synchronous counter you can count any pattern, you can generate any pattern. That is the another advantage of your synchronous counter over asynchronous. So this is a mode for irregular counter, and you have to count 0, 2, 3, 1 and it will repeat. So how to design the circuit for this type of irregular counter? So here you have to finish this table first. See here what is that given pattern? 0, 2, 2 to 3, then 1. Then it will repeat the counting. Okay, so in the present state we can represent as AN BN, next as AN plus 1 BN plus 1. Here it is 0 0 0 1 1 0 1 1. You have to write all that bit pattern in order 0 0 0 1 1 0 1 1. And see 0 0, then where to go? What is the next state? Next state should be 2 from the given question. 0, next should be 2. So in the next stage you have to write 1 0 instead of 1. And for 0 1, if it is 1, next stage should be 0. So here it is 0 0. And here 1 0, 2. 2 means from the question or in the given pattern, after 2 it will go to 3. So the next state is 3 1 1. And if it is 3, the next state is 1 0 1. So refer that here it is implementing using which gate? D flip-flop. Okay, not gate, D flip-flop. So you have to refer the D flip-flop's excitation table and fill these two columns. What is the excitation table of D? You don't need to refer. Whatever value is possible in this output, that will directly form that D input. That means you have to directly copy that AN plus 1 column as your DA, Bn plus 1 column as your DB. Now you can simplify using K-map and you will get an expression for DA and DB. DA is Bn bar and DB equal to An. So you can draw the circuit. You can connect DA as Bn complement. Here it is Bn complement. And what is DB? DB is An. And you have to, don't forget to connect this external clock pulse, the common external clock pulse to both the flip-flops. Okay. Next problem is a lockout condition. Sometimes in certain synchronous counters, sometimes the counter will enter into certain unwanted or useless state. And it can't come out from that state and it can't continue that counting. That case is known as lock-in condition. Suppose you have to design or you have one mode 6 counter and usually it will count from 0 to 5 and it will repeat. And somehow certain situation this mode 6 counter enter into a state 6 and it is not possible by that counter to automatically come out from this irregular state. It will loop there. Okay, it won't continue further. It won't count further. So this is the case of lock-in condition. See, in mode 6, the 6 and 7 are invalid state. Sometimes that mode 6 counter will enter into this state by mistake, by some circuit fault. Then in that situation the lock-in condition will appear or it can't come out from the state. But in some cases or we have some solutions that is in certain case our counter can automatically come out from such unwanted state and it can continue that counting operation. How this possible? So we can design certain counters in that fashion so that it can automatically come out from that unwanted useless states and it can continue the counting. For that, suppose for that mode 6 counter, you know 0, 1, 2, 3, 4, 5 and it will come back to 0. This is the usual counting. Okay, and somehow or suppose you are initialized your counter with this value or this value. These are invalid state or useless state in case of mode 6 counter. Okay, so you have to automatically come from this unwanted state back to your valid state. How this possible? So for the design, for such self-correcting circuit, how to design? See, these are the possible states using 3 bits 0, 0 to 1, 1, 1. But you have to design mode 6 self-correcting counter. So you know from 0 it will go to 1, from 1 it will go to 2, 2 to 3 and 3 the next state will be 4, for the 4 the next state will be 5 and 5 next state is 0. Up to these all are that usual cases. And suppose your counter is initialized with value 6, what to do? You can set the next state as 0. Suppose this counter is now present in 7th 111th state, you can set the next state as 0. Then it will automatically come back to the state and continue that counting operation. So this is the self-correction operation. And exactly like the previous case, you can refer that excitation table and fill that entries for all that JC, KC, JB, KB, JA, KA inputs and simplify that K-maps and get that minimized expression for all that inputs and draw the circuit. And don't forget to put that common external clock to all the 3. Synchronously connect that external clock to all the 3. And what is JA? JA and KA, here it is derived as CN bar or BN bar and KA is 1. So you have to connect exactly like this. Here it is J these two all together and the output is connected to JA and KA equal to 1. Similarly for JB and KB, these are the expression, and for JC and KC, these are the expression. You have to use different gates to implement that input combinations. Okay, so this is that self-correcting mode 6 synchronous counter.